Welcome to Chapter 3, where we explore the extreme world of supercritical water. While supercritical Co-2 operates under mild, accessible conditions, supercritical water exists at the opposite end of the spectrum. We're talking about temperatures of 374 degrees Celsius and pressures exceeding 22 megapascals. These extreme conditions fundamentally transform water's properties, turning our familiar polar solvent into something completely different. Supercritical water becomes a powerful tool for oxidizing hazardous wastes, synthesizing materials, and destroying the most persistent pollutants on Earth. The difference between supercritical water and supercritical Co-2 is dramatic. Co-2 becomes supercritical at just 31 degrees Celsius, essentially room temperature. Supercritical water requires heating to 374 degrees. That's 12 times hotter on the absolute temperature scale. The critical pressure of water is 22 megapascals, about 3 times higher than Co-2. These extreme requirements arise from water's strong hydrogen bonding network, which takes enormous energy to overcome. While this makes supercritical water technology more challenging and expensive, it also enables applications impossible with milder supercritical fluids, particularly the complete destruction of hazardous organic compounds. Perhaps the most dramatic change in supercritical water is the collapse of its dielectric constant. Normal water at room temperature has a dielectric constant of about 78.5, making it an excellent polar solvent that dissolves ionic compounds. As you heat water toward the critical point, this value plummets. At 400 degrees Celsius and 25 megapascals, the dielectric constant falls to just 2 to 6, comparable to nonpolar organic solvents like hexane. This happens because high thermal energy prevents water molecules from orienting in response to electric fields, and the reduced density means fewer molecules per volume. The result is water that behaves like an organic solvent. This property change creates remarkable opposite behavior. Normal water dissolves salts readily. Sodium chloride, for example, reaches 360 grams per liter. But supercritical water can dissolve less than 100 parts per million of the same salt. It simply precipitates out. Meanwhile, organic compounds that are practically insoluble in normal water become completely miscible with supercritical water. Benzene, toluene, even heavy oils mix homogeneously. Gases like oxygen and nitrogen, which have limited solubility in normal water, become completely miscible above the critical point. Supercritical water is essentially opposite water. It dissolves what normal water can't and precipitates what normal water dissolves easily. Operating under supercritical water conditions presents severe engineering challenges. The combination of high temperature, oxidizing conditions, and dissolved species creates one of the most corrosive environments known to engineering. Multiple corrosion mechanisms attack materials simultaneously: general oxidation, pitting corrosion from halide ions, stress corrosion cracking, and erosion from precipitating salts. Even noble metals like gold and platinum can corrode under these conditions. Materials must be carefully selected, with nickel-based superalloys like hastelloy and inconel commonly used, along with titanium for specific applications and ceramic liners for the most aggressive feeds. Supercritical water oxidation, or SCWO, harnesses these unique properties for complete destruction of hazardous organic wastes. The process works by mixing organic waste, water, and oxygen, then heating the mixture above the critical point. Under these conditions, organic compounds and oxygen are completely miscible, enabling homogeneous oxidation without mass transfer limitations. Reactions complete in just 5 to 60 seconds. Organic carbon converts completely to carbon dioxide. Nitrogen becomes nitrogen gas, not harmful nitrogen oxides, because temperatures are below thermal NOx formation. Chlorine, sulfur, and other heteroatoms convert to acids that can be neutralized. Destruction efficiencies exceed 99.99% for most compounds. One of the most important applications of SCWO is destroying PFAS, the per- and polyfluoroalkyl substances often called forever chemicals. These compounds have carbon-fluorine bonds at 485 kilojoules per mole, among the strongest bonds in organic chemistry. They don't break down naturally, they bioaccumulate, and they're found in the blood of 97% of Americans. SCWO at 550 to 600 degrees Celsius for 60 to 120 seconds achieves greater than 99.99% destruction of these compounds, verified by the US EPA in 2023. The fluorine is released as hydrogen fluoride and immediately neutralized to calcium fluoride, a stable mineral. Several commercial facilities are now operating. SCWO offers significant advantages over traditional incineration for hazardous waste. Operating temperatures are 380 to 600 degrees Celsius versus 850 to 1200 for incinerators. Because temperatures stay below nitrogen oxide formation thresholds, SCWO produces no NOx emissions. Without a gas phase, no dioxins or furans can reform, a significant problem with incinerators. No particulate emissions result because everything stays in the liquid phase. SCWO is actually ideal for wet wastes that would require energy-intensive drying before incineration. The compact, modular design enables on-site treatment. Public acceptance is generally higher than for incineration facilities. Beyond destruction, supercritical and near-critical water enable unique material synthesis. The enhanced transport properties, fast diffusion and low viscosity, combined with tunable solubility, create ideal conditions for controlled nanoparticle formation. Metal salt solutions injected into supercritical water experience rapid supersaturation, triggering nucleation. Quick quenching freezes particle size at the nanometer scale. This continuous flow process produces metal oxide nanoparticles like titanium dioxide for photocatalysis, zinc oxide for sensors, iron oxide for MRI contrast agents, and lithium iron phosphate for battery cathodes. The technique achieves excellent size control and high throughput. Let's summarize the key points about supercritical water. Its critical parameters are extreme, 374 degrees Celsius and 22 megapascals, requiring specialized equipment and materials. The dielectric constant collapses from 78 to just 2 to 6, fundamentally changing water's character. This creates opposite solubility behavior, dissolving organics while precipitating salts. SCWO achieves greater than 99.99% destruction of hazardous organics in just seconds. For PFAS forever chemicals, SCWO is one of the only proven destruction technologies with EPA verification. However, severe corrosion requires exotic materials and careful engineering. In Chapter 4, we'll explore how these supercritical fluid technologies translate into commercial industrial applications.